Okay, on to the last part of today's lesson, and keep in mind we are going to have a quiz today and we also have homework to do today. So the lesson may seem a little bit short, but do remember I'm doing stop and start, which adds length to the time, and that I'm also leaving you time to get the quiz done. Okay, and then should you get all of that done, you can also start the homework to cover all of the time. All right, so we've been talking about this uniform distribution, and the uniform distribution, when we interpret it through the lens of area, is that the length or the height of that rectangle stays the same. It doesn't fluctuate. It doesn't move up and down. It's just a horizontal straight line. Okay? These techniques that we're discussing today can only be done when the probability is equally likely all the way through, like in the rectangles that we drew. So here is an equally likely situation. It's equally likely how long a baby will smile for. So someone had a lot of free time and they recorded 55 smiling times for babies. And that's a pretty cool thing to do because the world can be a little ugly every now and then. And a smiling baby has a way of making the world a better place. So all of these scores are put in. And then we start thinking to ourselves, well, they're all equally likely. It's equally likely that the baby's going to smile at any point in time. But how do I know what scores to use for the rectangle? Well, let's just think about that for a little bit. Let's take a step back. Let X be the length in seconds of an 8-week-old baby's smile. So with the notation, we're going to use uniform distribution and we're going to use the term U and then AB. Now, what is this A and B? A and B is, if we just go back for 1 second, the A is going to be the lowest value on this chart and B is the highest value on the chart. That way we have a beginning and an ending point for our rectangle, okay? It doesn't make any sense to have a 0 as a beginning point because in each case, it's when the baby smiled and we didn't do anything until the baby smiled and then we measured the length of time that the baby smiled for. So like on the other ones, we always started with 0. That's not the case now. So we find the lowest score and we think of that as our beginning point, which we refer to as A. And then we find the highest score and we refer to that as B. So if you wanted to write in your own words, it would be very likely that you could write U for uniform distribution of lowest score, highest score, okay? Or lowest value, highest value, if you wanted to write it all out. But in math, we tend to not want to write out the whole terminology, lowest value, highest value. So we just call the lowest value A and the highest value B. It's a little tricky to remember because you're not given a variable that sounds like lowest value and another term for highest value. So just remember A is lowest value, B is the highest value. So the probability density function, that's the same as before. It's 1 over B minus A. Now, if we go back to the prior diagrams, in every case, or let's remember the one where the probability was 1/8 and that formed the width. It was 1/8 because the seconds went from 0 to 8, okay? Or the data went from 0 to 8. In this case, the data is not going from 0 to 8. The data is going from the shortest smiling time of the baby to the highest smiling time of the baby. So when I want to calculate that, I've got to do the longest time minus the shortest time, and then it's 1 over. So in the first diagram we saw, where the length of the base, the horizontal length was 8, we knew that the probability was 1 over 8. Well, we need to figure out what this length is going to be for this rectangle, and the length is going to be whatever the highest score minus the lowest score is going to be. So the probability is going to be 1 over that highest score minus lowest score. And then, of course, in this example, we're going from 0 to 23, all right? So that's how we do our calculations, all right? Emphasis on the fact that uniform distribution, X, is pretty much the same thing as saying it's the uniform distribution of the lowest value to the highest value. In this particular problem, reading off that chart, I get from 0 to 23. So the probability will be 1/23rd, and then the length would go 0, 1, 2, 3, all the way up to 23. Now, the next thing is that you are asked to calculate the mean, and you are asked to calculate the standard deviation. Now, here's the good news. The good news is that the mean formula is just like every other mean you ever did, and what you do is you add them up and divide by 2 for the average. Now, you're not going to add up every single score and divide by 55. We're going to make it easier than that. We're going to take the lowest score and the highest score and divide by 2, okay? And the standard deviation is going to be the square root of b minus a squared, all in parentheses, and then divided by 12. And then you take the square root after you do b minus a squared and divide by 12. Okay, so for this problem, the theoretical mean and the standard deviation work out to be, for the mean, the lowest score is 0, that's the A. The B is the highest score, add them up, that's 23 divided by 2. I get 11.5. And then the standard deviation of this particular sample going on here is going to be 6.64 seconds, because I take the square root of 23 squared divided by 12. Okay, so notice the theoretical mean and the standard deviation are close to the sample mean and the standard deviation in this example. That's worth noting, that they come out very, very close one to another. All right, one of the key takeaways here is that this from 0 to 23 is the lowest score to the highest score, and that's how we find the length of the rectangle that we're getting. And then the probability density function will always be 1 over whatever that worked out to. So let's just say instead of 23 and 0 being the highest and lowest, let's say it was 20 and 5. Then that would make this 1 over 15, because my rectangle would go from 5 to 20. All right, so let's take a look. Please note, they give you the formulas. So you will be given formulas on anything you have to figure out. You don't have to commit them to memory. So the data that follow are the number of passengers on 35 different charter fishing boats. The sample mean is 7.9 and the sample standard deviation is 4.33. The data follow a uniform distribution. That means we can make it like a rectangle, where all values between and including 0 and 14 are equally likely. So lowest value 0, highest value 14, equally likely. That means horizontal bar all the way across. State the values of A and B. A and B will be the highest and the lowest scores here. And write the distribution in proper notation and calculate theoretical mean and standard deviation. Okay? So first, let's write it like we did before, where we said that X was like uniform distribution, U, and then parenthesis, comma, parenthesis. Okay. So, doing that, here's your two formulas. Okay. Well, I should say doing that, my correct way to represent this is that X is pretty much the same thing as, or we're going to use the terminology, uniform distribution, U, and then the lowest score up on that chart, which is 0, and the highest score, which is 14. So it's a uniform distribution from 0 to 14. And by the way, what does that mean the probability will be? 1/14, right? Okay. Now, it asked us also to figure out the theoretical mean and the standard deviation for this uniform distribution. Here are the formulas. I said before, you're going to be given it, so here they are. Just do the highest plus the lowest divided by 2 to get, we call that letter mu, and that letter mu represents the mean for a uniform distribution. And then, of course, we have the standard deviation formula. So that works out to be, for mu, it's the low point, which is what A represents, the high point, which is what B represents, 0 plus 14 divided by 2, which gives me 7. And for the standard deviation purposes, we're going to do the subtract the highest score minus the lowest score, which is 14 minus 0, and then square it, divide by 12, and get your square root of that. And when I do that, I get 4.04. Just a quick way to put this in the graphing calculator, hit second x squared, that gives you the square root symbol, and then hit alpha y equals, that gives you the fraction. Go up in the top, enter the parentheses, and everything straight across, and then go down to the bottom, enter the 12, and you will get your value. Okay? So calculating mu, or this the mean, and then also calculating the standard deviation, very, very, very simple. Super simple. All you got to do is find the lowest value, the highest value, add them up, divide by 2. And then in the case of the standard deviation formula, subtract them, square them, divide by 12, everything under a radical. So that's really easy to do. And then, of course, we understand that the way we note this is the U for uniform distribution, and then smallest, lowest score, lowest data, highest data, whatever you want to say. I always say score. That's the terminology that you need to be able to do, okay? Conceptually speaking, we need to understand how this rectangle works. So here's a couple of questions that do that. What's the probability that a random chosen 8-week-old baby smiles between 2 and 18 seconds? Now, this goes back to the problem where we said that it's equally likely over 23 seconds. All right, so I'm going to give you a minute to do that. Start using stop and start. I'll give you the correct answer in just a minute with a little bit more explanation. Okay, so here's my rectangle, and we know it's from 0 to 23. And this is a uniform distribution, and it's discrete, so the area under that rectangle has to be 1. Okay, so that means that the height of this rectangle has to be what? I should say the width of the rectangle, the height on the graph. It needs to be 1 over 23, okay? Because all events are equally likely, and there's 23 different events. And then, if I want to find the probability that it's between 2 and 18 seconds, that means I'm going to mark off this rectangle that begins at 2 and ends at 18 to form the length of the rectangle. So 18 minus 2 is 16. As we discussed before, it's like the A would be 2 and the B would be 18, because the A is the lowest value, the B is the highest value. Okay, so with that in mind, what probability goes here? Well, we just discussed that. That was 1 over 23. So the probability that the result is between 2 and 18, it's a rectangle. We said that the probability equals the area. Remember, that was a really big part of a few slides ago. So 18 minus 2 is 16 times 1/23. 16 is the length of the rectangle. 1/23 is the width of the rectangle. Multiplying them, and I get 16/23. So that's what the probability is. Okay? If for some reason you did not get that right, I would rewatch this section, because I'm very confident that you can understand this, and I want to make sure that my explanation is satisfactory. Okay? All right. So the next thing it asks for is to find the 90th percentile for the 8-week-old baby's smiling time. Let's go through this step by step, okay? Because percentiles gave us a little bit of a problem when we covered them before the first test. So the 90th percentile converts to a decimal 0.9. And if you look at it in terms of the rectangle, then that means I want to have an area of 0.9. So what, take away 0, multiplied by 1/23 gives me 0.9. And the answer to that is 20.7. Or you could just say to yourself, what is the what is 90% of 23? And that would give you 20.7. Because this is continuous all the way through, and you could get the decimal 20.7 would work. If it was always individual scores, then it would be 21. Remember, the area in uniform continuous distributions is 1, and 90% of that area would be 0.9. So that would make the length 0.9. Okay. Next up, the amount of time in minutes that a person must wait for a bus is uniformly distributed. Ding, 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 ding. To me, that means rectangle, length, width, height, everything, every probability is the same. All those things are ruminating through my mind. It's uniformly distributed between 0 and 15. Ding, 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 ding. A, 0, B, 15. All of those things are rocking through my mind. about what we've gotten out of today's lesson. 3 things to do. What's the probability that a person waits fewer than 12.5 minutes? I'm saying to myself, I better do a rectangle. Next, on the average, how long must a person wait? The average is mu. And remember, we have a formula for that. It's a plus b divided by 2. And the standard deviation, which is the square root of b minus a parentheses squared over 12. 90% of the time, the person must, 90% of the time a person must wait falls below what value? So that's another way of asking for the 90th percentile. Let's rock and go through these answers one by one. A little stop and start time. Do them all, and then I'll go over them with you. Okay. So we start with part A, and then we get into B and C. Okay. When I look at this, I say, okay, well, X is the number of minutes a person has to wait for a bus. We said that A is the lowest value, that's 0. B is the highest value, that's 15. And if we use our notation, X is similar to or tilde, it's pretty much the same as. Another way to represent it is U for uniform distribution, 0, 15. Don't forget the parentheses and the comma in between. The probability density function would be f of x is 1 over 15 minus 0. And that's got to be 1/15 for all the way through. Okay. Then I draw a graph. We go from 0 to 15 on the graph. And we know that the probability is 1/15 because everything is uniformly distributed, equally probable. And then I have to do length times width, which is a length in this purple rectangle of 12.5 times the width, which is 1/15. Another way to look at it is b minus a, the highest value minus the lowest value, which is 12.5, times 1/15, which is 0.8333. So the probability that a person waits less than 12.5 minutes is 0.8333. Really goes on forever and ever. And you could, if you rounded it off, just say to nearest hundredth, 0.83 or 0.83 with the 3 repeating. Okay. Key features here. We knew the probability had to be 1/15 because everything is uniformly distributed from 0 to 15. So that horizontal line tells me all probabilities are the same. Since there's 15 different possibles all the way through, they're 1/15 each. And the length of the rectangle in this case has to be 12.5 because I'm looking for 12.5 or less. That's what fewer means. Okay. Now, as far as the rest of the calculations go, we said to find mu, or the mean for this sample, it's just a plus b over 2, which is 15 plus 0 over 2, which is 7.5. So on average, a person waits about 7.5 minutes for the bus. And the standard deviation is the square root of b minus a. B highest value, a lowest value. That's 15 minus 0. I square it, I divide by 12, and then I take the square root, and I get 4.3. So that standard deviation is 4.3 minutes. Finding the 90th percentile. Draw the graph, which we just did a minute ago. But instead of putting the mark now at 12.5, we're going to figure out where that mark goes. But we want to cover 90% of that rectangle. So, in other words, one end of it's 0. That's the low end. We're going to subtract that out. So I get k times 1/15 has to equal 0.9. So cross multiplying or dividing by 1/15, however you want to look at it. I get 15 times 0.9, and that's going to equal 13.5. Sometimes they use the terminology k is the critical value. It gets you the percentile. So the 90th percentile is 13.5 minutes. It sounds very confusing, but it's really pretty simple. Each probability is 1/15. If I take that and I multiply it by this value that gets me 0.9, then all I have to do is divide both sides by 1/15, which is the same as multiplying 0.9 by 15. And that gets me a critical value of 13.5, and that says the 90th percentile is at 13.5 minutes. 90% of the time, a person will wait 13.5 minutes or less. Okay, so we have now covered our uniform distribution work for today. Not too bad. I think it's understandable. I think you should be good with it. Personally, I feel like there should be a little bit more. Like there should be a little bit more coming. And it seems almost too easy. But this is it. We don't go any further with it than this. In chapter 5, we only do the first 2 sections. So there's no more of that concentrates on this particular work. If you can handle the mean, they give you the formula, a plus b over 2. The standard deviation, they give you the formula, square root b minus a squared over 12. And how to figure out a percentile. You can do everything that the second part of this lesson wants you to do. And if you can draw the rectangle, find that uniform probability distribution, like 1/8 before or 1/15 in this problem, and then box in the part of the rectangle that you want to work with. Remember, area is the same as probability. Length times width of the area gets you the probability. If you can do that, you've done everything that this lesson wants you to do. Okay, have a good one.